Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is Gary Carlson. He's the Executive Director of BWRC. I'm not going to go through his bio, which you all have already seen. I just want to make the point that of a lot of the labs that I've seen doing research in wireless, I think the BWRC is one of the best or the topmost, doing great work. So it's a real pleasure to have him here and tell us in general terms of all the different activities that are going on there in his research center. So Gary.
Thank you very much, Victor, and very pleased to be here today. My first visit to Microsoft Research. So I'm going to spend the next hour or so telling you about the Berkeley Wireless Research Center. Victor attended one of our research retreats about a year ago, and so I'm the executive director of BWRC, and so I'll spend a few minutes in the beginning talking about what we do, what our research focus is, kind of what our operating model is, so to speak, and then go into some of the specific research that we do in spectrum utilization, led by Professor Bob Broderson and Ali Niknejad, low energy sensor networks, led by Professor Jan Rabai and Paul Wright, analog and digital circuits by Professor Bora Nikolic, and then reconfigurable computing. I'll touch on that, led by Professor John Worsnick. So you're probably already getting a sense that we're pretty hardware oriented and wondering what I'm doing here. But I know that there's a lot of interest within Microsoft on sort of directions in hardware and sort of enabling platforms and so on and so forth. So I'll try to emphasize that aspect of what we do. So who is BWRC? What do we do? And we're a partnership of UC Berkeley researchers, industry, and government. So all of us are UC Berkeley employees, faculty, staff, graduate students. We're not some separate organization that just uses the word Berkeley. We're all part of the University of California. We have 17 members that are part of our center, and you can see the list there. They're divided into two categories, what we call participating members, and we use that name because we actually encourage all our members to participate. We have many of the companies have resident researchers who are at our center from anywhere from a year to some who come back and forth on maybe for a week or a month, or many of our members are local in the Bay Area, and they come on a daily basis. But participation and becoming part of the research team is really what we encourage among our members, and we try to bring together the best of university research and industrial research, and that has worked really well. We also are sponsored by a number of government agencies that you're probably all familiar with, California Energy Commission as well. That's funding a lot of the sensor network embedded computing work. It's a pretty large program. We have 60 graduate students and almost a dozen faculty. We have our own center that's specifically dedicated for this group. Prior to establishing this wireless research center, there was certainly a lot of wireless research going on at Berkeley, but it just sort of spread out among a number of different faculty and different buildings and so on and so forth. So we really felt a need, starting in '98, to have our own facility, which is just on the edge of campus. And the only reason we're not on campus is because to find new space and on campus probably takes a decade or more. So we thought we'd be entrepreneurs like many of our sponsors, and so we were able, from the time we got commitments from the original 7 companies in 1998, in 15 months we had the center operational, and we opened up in 1999. So as I mentioned, we really encourage our members to participate, get involved with our research. Our research focus, of course, being university research, is pre-competitive, so we try to stay ahead of the companies that are working with us, and our focus is on determining relationships between theoretical and algorithmic advances for radio systems on a chip. So, if you really look at the roots of our faculty and the roots of our research, we're integrated circuit people. We're hardware people. We're interested in how advanced communication systems, algorithms, protocols can be efficiently translated onto silicon platforms. So to understand the trade-offs between various implementation architectures, so we spend a lot of time thinking about signal processing architectures for future communication systems. I know from discussions with Victor that there's a lot of interest in cognitive radios, for example. And we know that if cognitive radios are ever going to be used extensively, they're going to have to support a very large amount of signal processing, sensing, spectrum, and to be able to do that in a very performance, power, and cost optimized basis. So I'll spend some time talking about that. From an operational standpoint, it's important to understand how we deal with IP. IP can oftentimes be a stumbling block. And from my experience, and I spent most of my career in industry before I joined the BWRC, IP is sort of a bimodal sort of situation. It's either very simple or it's very complex, and there seems like there's little middle ground. And so we've chosen the very simple approach, and by publicizing the results of our research. Now, our member companies do get some preferential advantage, but it's only for 6 months. And then we put everything into the public domain. And so if you go to our website, and it's a very rich website, you'll see how we do that. Some people say, well, gee, 6 months, that's not much. But the real benefit of being involved with us is getting involved. And we basically open our doors to researchers and invite them to come and get involved with us. And we all understand that in our work, the devil's really in the details, and really getting involved with us and understanding the details is where the real benefit in becoming part of BWRC is. We are fortunate to some extent because of the size and our previous accomplishments to be supported by a number of companies, particularly with regard to wafer foundry. And so we are able to build proof of concept prototypes for all of our projects. All students get involved in building some kind of a chip prototype. And we have a laboratory for testing them. ST Microelectronics is our primary wafer foundry, and our chips are fabricated in their new fab in Crolles, France, which is the joint venture of Motorola, Philips, and ST. So we've been doing 90 nanometer CMOS chips for about a year now at the Crolles ST plant, and we also have relationships with TSMC and IBM. We've done some work in silicon germanium by CMOS, but most of our focus is on CMOS. We're believers that Moore's law solves a lot of problems because we get ever increasing complexity and ever shrinking costs, and to some extent the problem is now becoming how do you utilize all that complexity in some meaningful, efficient fashion. Okay, so let's talk a little bit about when you say wireless today is a pretty big space, and where do we focus our work? And so if you think about the wireless landscape as being something where we look at data rate and range, and so where we've got wide area networks, cellular, metropolitan area networks, LANs, personal area networks, like so. And you remember that I said, well, we're doing pre-competitive research, so that pretty much keeps us out of the cellular area. And so our focus, we have two focuses. One is driven by sort of more bits per second in this sort of land space. When we first started the center, we thought, what we really need to do is focus on spectral efficiency. People pay a lot of money for spectrum, and so how to efficiently utilize it should be really important. But as we have pursued that, we came to understand that there actually is a lot of available spectrum. It's just how do you effectively use it? So it's kind of gone into more bits per second rather than more bits per second per hertz. It's a bit of a subtlety. But what that means is exploring the use of new spectrum. So you may be aware that at 60 gigahertz, there's 7 gigahertz of contiguous bandwidth available in the unlicensed band. It's more bandwidth than virtually all wireless services, including television, broadcast, radio, used today. There's some problems, of course, at dealing with microwave or millimeter wave frequencies. The primary problem is cost. It's very costly to build circuits that operate in those ranges. So we're exploring the use of CMOS circuits, and I'll talk about that. We're really proud of what we've accomplished there. It's really breakthrough technology. And then recycling spectrum, sort of cognitive radios, and we'll talk about that. There's some surprising results that when you stick an antenna up in the air and you sniff what's really out there versus what's shown on the FCC charts, it's pretty interesting. And then there's some underlay are sort of systems that operate below the noise that you can recover through processing gain, like ultra-wideband. There's a lot of interest these days in ultra-wideband for broadband consumer applications. I'm sure some of you are involved in. And then the other thrust is sort of cheaper bits. Not a particularly elegant name, but the idea here is building systems where cost is really the driver rather than bandwidth, and we call that ubiquitous embedded embedded systems, or primarily sensor networks. So here, the ultra low cost, ultra low power, and small size are the driving determinants. Sort of the holy grail is building devices that are energy self-sufficient. So you manufacture this device, it gets deployed in some product, maybe embedded into products. We've had people that build ceiling systems like these ceiling tiles. Armstrong Industries, one of the leaders. They want to embed sensors into those when they manufacture the tiles. And then when the tiles are installed, question?
If they're really energy self-sufficient, how do you shut them off when the FCC says they want the bandwidth? That's a good question. They don't have very long range, so that's one blessing. But sort of the operating scenario is they get built into products and they're put in boxes and shipped in trucks, and they may communicate with some neighbors while they're in that truck. There are certainly a lot of issues that are yet to be resolved. And once the system's deployed, then it's an ad hoc system that begins to build a network and to send data upstream. That's the concept. And they should have an ultimate lifetime of maybe 20 years, kind of the life of the product. And that's the holy grail. You don't typically get there by some fixed battery. The approach that we've been pursuing is a battery with energy scavenging to supplement the battery and keep it going. Okay, another way to look at this is spectrum utilization, embedded wireless. So there's a lot of work on communications algorithms, signal processing algorithms, signal processing architectures that support this area. Low power systems, protocols, networking, statistical design has become important as we've pursued this, because as you drive power down, you're driving supply voltages down, you're starting to operate near the edge of what processes are capable of doing, and then at the same time, process feature sizes are moving down in the 65 nanometer range. So statistical design is becoming important. So this is really hardcore hardware design. but a very interesting area in our field. We have a significant effort associated with design methodologies and design flows. I won't talk about that today. Reconfigurable computing is something that we're interested in because we believe that future signal processing architectures are going to be more reconfigurable than fixed or software defined processors because of the energy efficiency issue. We're circuits people too. We build prototype chips. Very interested in RF and millimeter waves, CMOS, low power digital, and analog and digital converters. I mentioned that we build prototype chips. We also build various kinds of test beds. So we have, and I'll mention that we've built these FPGA-based emulation engines that allow us to do emulation of real-time, cycle-accurate, bit-true emulations of communication systems, where we have analog interfaces and we can connect real radios. So we're building a system right now to support multiple antennas and systems and cognitive radio test beds. Okay, so now I'm gonna move down into some of the specific projects, and so first we'll talk about this exploiting new spectra. So for hardware people, this is a really exciting result, and I sort of skipped to the bottom line. About a year and a half ago, we presented the paper at ISSCC on the world's first 60 gigahertz CMOS low noise amplifier. And this was a real breakthrough. I think prior to this time, the only thing that was reported was 30 gigahertz. A lot of work went into developing a design methodology that gives us repeatable results for microwave CMOS designs. And I'll just touch on a few of these things. But this is a breakthrough in the sense that it enables this 60 gigahertz band to start being used for low-cost communications. Not long-range communications because of the power and loss and so on and so forth. Question?
Just curious, what's the noise figure for?
This first device had a noise. Let's see, do I have it here?
So you're
11 dB gain. The noise figure was not particularly good on this first device. I think it was around 7 dB. We've already got some designs now. We're moving into 90 nanometer that are around 3 or 4 dB.
Oh, that would be impressive if you can do it.
Yeah.
Maybe up to.
We have another project that we recently started up, a little bit lower frequency, but to build a CMOS replacement for broadcast satellite receivers. If you're familiar with that, that requires a noise figure around 1 dB. So we think we can do that. That's only, I think it's 14 gigahertz.
For wireless band, which I assume a lot of the applications are going to go into.
Yes.
60 gigahertz. I'm not sure you really need that strict noise figure.
That's right. That's right.
But yeah, for direct broadcast.
We're interested in wireless LAN. We're interested in automotive radar, collision avoidance, other applications. So there are certainly a lot of challenges. We're not done with this. This was one of our first devices. So power, noise, antennas are a big issue. You know, antennas scale with wavelength. Antennas are only millimeter size in this case, and so there's antennas. It's very difficult to achieve high gain antennas at this frequency because the antenna is so small it doesn't capture much energy. So the fact that they're small, we're looking into antenna arrays. Victor mentioned that there were some that are possibly interested in antenna arrays. So it's pretty straightforward to build an array of antennas, and then I'll talk about electronically switch them so that you can then you can do beam steering and overcome the lossy nature of antennas at this frequency. And of course, packaging. You don't put devices like this in any old plastic package and bond it on a PCB.
You're going to have a 2D array. If you have a CMOS process, how do you do 3D beam steering?
We don't do we won't do. It'll just be 2D. It'll be a patch antenna array on a substrate. That's.
I see.
Yeah.
So if the tile is a little bit crooked, then
that's
go
right.
for it.
That's right.
All right.
So it would just be two-dimensional.
I see.
I mean, it could be extended with a more complex structure. And I'll talk a little bit more about this. Okay, well, there was a lot of work to do in terms of understanding transistor design, and I know I'm driving even farther down into hardware design, but we're fortunate at Berkeley to have people who are modeling and simulation experts. The BCM model started at Berkeley is one of the worldwide standard models used in CMOS design, and so when we started in this, we were interested to see that 130 nanometer CMOS devices have a Fmax of about 130 gigahertz. So we could achieve 6 dB gain at 60 gigahertz. But there are a lot of other problems. How do you deal with reactive components? In order to build a radio frequency circuit, you need some inductors and capacitors. And we've achieved that through the use of transmission lines. So on the chip, we actually build integrated transmission lines. We use coplanar transmission lines. So that if you looked at that previous slide, you might have noticed the transmission line nature of the device. The nice thing about devices like this is we're capable of realizing precise and small reactances that are inherently scalable and defined by mask geometries in the same way that we define transistor structures. The coplanar structure is much more amenable to our process than this more popular microstrip design because of oxide thicknesses and so on and so forth. So we're able to build really nice filters using just transmission line designs. And here's an example of a 30 gigahertz passband filter. And because we spent a lot of time modeling devices and we were able to get very good predictability between measurement and, in fact, we've been accused of fudging the numbers so they look so good. But in fact, what we started off doing is using this HFSS program. It's made by Ansoft, and it's an E&M simulation program. So you sit down and you model in electromagnetic field theory the structure. It's very computationally intensive and very slow, but you really understand what's going on. Then you take those models and you put them into a lumped simulation model, ADS, made by Agilent. And then you correlate the two, and that's been our strategy, our design flow strategy. And through that process, and then build test chips, calibrate the whole thing, go through that loop, we get very good results, very good predictability. In fact, maybe better than what people are able to do when they design like 802.11a wireless LAN transceivers at 5 gigahertz, because 5 gigahertz, you're kind of right at the edge of lumped circuit design. Here, we're into fully distributed circuit design, and if you do it right, the predictability is quite good. So here's the first CMOS front end we built with that same amplifier, a mixer. You can see these transmission lines here, and a 40 gigahertz LO buffer. So this device so we convert 60 gigahertz down to 20 gigahertz with 7 dB a gain. It was our first attempt. It had some problems, noise problems, and so on and so forth, but it demonstrated the feasibility of this. We're also now, so to attack some of these power and noise issues, we're moving into 90 nanometer, and it's just a test chip. We have some designs, LNA designs. So now, to go answer your question, this is a simulation. 5.5 dB, and we've cut the power about in half from that previous design. And these transmission lines, the models for transmission lines are actually measured results from derived from previous those test chip measurements. And then there's also, so I didn't say anything yet about power amplifiers, but if we're going to build a communication system, obviously we need power amplifiers as well. So here is a simulated design that will be going into fab. About 15% efficiency, which is not bad. Typical cell phone silicon-based power amplifiers are in the maybe 25% range. So there's still a lot of work to do here. We're not as far along on power amplifier design as we are in low noise amplifiers and receivers.
So you don't think we need gallium arsenide for something like that?
Well, gallium arsenide, of course, would be a big benefit.
Expensive.
But as I said earlier,
Yeah.
you know, as researchers, we want to push the CMOS envelope.
We would like that.
Yeah, yeah. And I'll talk a little bit about how we overcome the fact that we don't get very much output power. And trying to build a real power amplifier at this frequency is very difficult. Okay, so that'll get into the moldable antenna stuff in just a minute. So, antennas are a big issue at this frequency. Some years ago, Hewlett-Packard, Agilent, built a 60 gigahertz 1 gigabit full duplex wireless LAN system. And they built it in Agilent Laboratories, or HP Laboratories, and it was a very, very nice system. All built out of indium phosphide compound semiconductor MMIC chips, and, well, they never marketed because it was much too expensive. But it was quite interesting. And the antennas they built were these sort of quasi-optical dishes. And I think it had a couple kilometer range, and it was quite nice, but $5,000, I think, per terminal end, and really didn't make sense. Whoop. Okay, so overcoming this antenna gain problem is an issue, and so we've been pursuing beam forming through moldable antennas, and so the idea here is by weighting each of these antennas in amplitude and phase, we can direct the beam and electronically steer the beam. So it's like a phased array antenna system that's used in radar and other applications. On the transmission side, this is really a nice benefit. We can use spatial combining. So if you think about it, each one of these as a separate transmitter, and then by properly controlling the phase and amplitude, we can spatially combine and steer the energy in a transmission mode. So in receiving, we can steer our receiver so it blocks interferers or attenuates interferers, and we can transmit all our energy. So we overcome. There's two benefits in that, and I'll get into that in just a minute. So here's the idea. Typical omnidirectional antennas. Interferers have the same signal strength as the desired signal. But if we can build a multiple antenna system and direct the beam, then we attenuate interferers and have higher gain from the desired signal source. The architecture we're pursuing looks something like this, with the transmit side and separate weights, separate power amplifiers, antennas, which can be switched between a transmit mode or in the receive mode. Again, weighting the various antennas, mixing down in the receive signal. So this project is focused at how precisely do we have to make these weights? And at first, you think, this is going to be a very difficult accuracy problem, and that's not very amenable to integration. We like binary things, on or off. And so let me just skip ahead. As it turns out, if you look at the case for, let's say, 16 antennas, and we quantize the weighting between either +1 or inversion or 0. And so the weighting of each one of those antennas can be either +1, -1, or 0. But you spatially combine them, it turns out that you can get quite good accuracy, and you can see only a few degree error in the angle and the gain, only maybe a dB or two loss from the case where you have infinite precision in the phase and amplitude weighting. That's really good news. We can build these phase shifters just out of inverters, gates that are either it's an inverter or a pass gate. So we have a test chip that we fabricated and are actually testing at the moment. I'll show you that in a minute. Oh, okay. So here's the test chip. This consists of 4 weighted channels. So now we get into the packaging issue. So how do we now? At first we thought, well, we'll put the antennas right on a chip, but silicon area is much too expensive to do that. So the antennas are on some kind of a substrate, either a high-frequency PCB. In this case, we're using a low-temperature co-fired ceramic substrate. So we have a cooperative effort going on with a research institute in Finland, VTT, which is a Finnish government research organization, which you might imagine has a big emphasis in wireless. And so they've got this LTCC technology, which allows us to bond a chip with, you may be familiar with this bump technology. So each bonding pad has a gold alloy bump on it, and that's directly attached to the LTCC substrate. Much of the way many large pinout circuits are bonded inside of a package these days. So we've worked with VTT to design a patch antennas, which looks something like this. So it has a differential drive from the CMOS circuit. Here's a picture of the actual substrate with 4 antennas. The chip hasn't been bonded on yet, but that's going on as we speak. And within a few months, we expect to publish the results of this work. This is a PhD work of one of our graduate students. So the expectation is that this kind of assembly technique will allow us to overcome the antenna gain problems at this frequency and address the assembly issues. So this is potentially a low-cost assembly technique. As I mentioned, it's the same assembly technique that's used today for high pin count integrated circuits. I'm not sure, but I think possibly, Intel, AMD processors. Certainly, if you look at FPGAs that have hundreds or 1,000 pins, they use this same technique, and they use standard pick and place technology can be used to assemble the die to the substrate. Question?
How do you normalize space? It looks like your transmission lines are different lengths there. You were
yeah, these
expanding on the idea of using amplitudes as a phase shifter, yet I see different.
Right. Well, the input looks like it's been not matched exactly. I'm not sure I know the answer to that question, but that's a yeah. There's you see, here's a little test antenna with some differential mismatching in the phasing. We do generate that scheme. Requires a generation of quadrature signals, and that's done through transmission line delays. So possibly some of that's what's going on here, but I'm not sure.
Off by whole wavelengths in terms of length, and since it's 14 by 15, that's possible. That would be okay.
Narrow band.
I can certainly follow up on that. Okay, so let's move on to cognitive radios and talk a bit about that. So if you've ever looked at one of these charts that the FCC puts out that shows frequency allocations, you can see that frequencies have been allocated basically from DC to light, and much of it's actually been licensed. But if you look, you put an antenna up in a spectrum analyzer, it's amazing what you see. And this is in Berkeley. I mean, I'm not trying to say this is true all over the world, but you see many people coming up with the same results. And it's not surprising if you really think about it. But so a lot of the spectrum's allocated, but a lot of it's not used. And the idea behind a cognitive radio is, could we design a radio that allows unlicensed users to share the spectrum with the primary or licensed users, okay? And to do that in a coexisting, non-interfering fashion. And amazingly, in the last several years, the FCC has kind of done a U-turn on us. I think the FCC has done a great job of marketing a scarce commodity, frequency spectra. But in fact, maybe it's not so scarce. And I think we've had people from FCC come to the center, and I think they're starting to develop a mindset that goes something like, maybe we can build electronic systems that are better and more efficient at negotiating bandwidth than subcommittees in Washington and IEEE committees meeting all around the world that take decades to decide how to utilize spectrum. Maybe we can do that dynamically.
What does the NAB say about all that?
What is it? Well, so we had a workshop in November, and we invited many people, and we had some, of course, there's a lot of interest in the university. I think there's a lot of interest here. There's a lot of interest in people who want to build new electronics communication systems. This would really be beautiful. But there are a lot of people sort of, I'll call them incumbents. The National Association of Broadcasters. We had Qualcomm, you might have noticed, is a member of our center. So we had a representative of Qualcomm. Well, their positions vary from very cautious to this is a very bad idea. And of course, okay, so we have a good relationship with Qualcomm. And it's not surprising that they voice great caution about this. The benefit of getting people like that involved in this is that they built real systems. They understand adjacent channel interferers. They understand a lot of issues that many of us don't. So, yeah, those who have been operating in licensed bands figure we paid for this. We don't want other people in our bands. And it's true. If you look at Qualcomm CDMA systems, they've squeezed every tenth of a dB out of those available channels to allow higher and higher spectrum efficiency. So if you start getting a bunch of these guys raising a noise floor, that's not good for them. But there's plenty of spectrum available where you don't have to. I mean, I think the idea is to go after the low-hanging fruit. And going into the cellular bands is not low-hanging fruit. The FCC has said, well, let's do some experimental work in the TV UHF band. There's a lot of excitement about that. We're kind of more interested out here. And you can see there's not much here. There's the UNII band, the 802.11a, and some other things. So this is a really interesting problem.
Is it true that some of the upper bands have this problem of stuff being allocated to essential services like the Army and all? So it's not about being free. It's just that they're worried that if somebody starts to operate, it would screw up the other ones.
Yep. So a lot of spectrum is allocated for public service and emergency response and government use, which has a low duty cycle use, but very high, needs high reliability. So there's this concept of sort of lights and siren kind of approach that, okay, if one of these public service guys come on the air, everybody vacates immediately. And there are solutions to a lot of these problems, but public service may only use those frequency bands 5 or 10% of the time. I mean, you think about police or fire, how often are they talking?
I understand. I think the problem is when these rules were set, a lot of the technology was not capable of doing a lot of the things we're talking about now.
That's exactly right. And that's why I mentioned the point about FCC. I think the FCC has woken up to the fact that that the same spectrum licensing strategy policy that's been applied for, I don't know, 50 years is not applicable now that we have technologies capable of doing some really dramatic things. Okay, so we're very interested in this. We had a workshop. There's a link to the workshop here. I'm not sure how I can activate the link. But anyway, we brought together, it was a full-day workshop. We had people from industry, from academia, Intel, Qualcomm, TI, and people who are participating in the IEEE groups, and so on. So, you know, the FCC has now defined a cognitive radio as a radio that can change its transmitter parameters based upon interaction with the environment in which it operates. That's kind of their definition. What that really means is that you've got to build a radio that can sense its environment, that can do some kind of cognition to identify who are the primary users, and then some kind of adaptation to utilize that frequency band in some opportunistic fashion. But the sensing problem is probably the most difficult problem. If you think about radio receivers, people are always interested in pushing the noise figure and the gain, you know, down, and so building the best receiver you can. So we're almost faced with the problem of building a cognitive radio that's as good as the best receiver out there, because we want to sense what kind of traffic might be there from incumbents. So that's a real difficult problem. Let me just talk a little bit about you know, what's going on in this regulatory and standards process. But you know, there's a lot of interest, as I mentioned, in academia and industry. We feel that there's a real need to bring together you know, industry and academia and to demonstrate to the FCC and to the you know, the various groups that you know, the national broadcasters and so on, what can be done and what's really feasible. And you know, the FCC is really focused on this TV UHF band. There's a lot of people. We had some speakers from Intel and Cadence who are looking at that. They think that there are some good business propositions for developing new services. That's kind of divided between two areas: fixed wireless access that the FCC has defined, and these are primarily professional installed services that would be fairly long range, kind of somewhat in competition with WiMAX, and more directed at rural applications where their connectivity is more difficult. And then the other application is portable devices, and this is one that people are much more interested in. And you know, couple-kilometer range, autonomous devices. There are many issues. Spectrum sensing is probably the key one that I mentioned. That's one that we're focused on from a research standpoint, and how to do spectrum sensing. I mean, you don't want to build a device that goes in and tries to demodulate every possible and identify it. That's much too cumbersome. You'd basically have to build a large number of receivers on a chip. So we're looking at other things like energy detectors, and then this is where our focus is on what's called a feature detector that exploits the modulation signal structure. So kind of a cyclostationary spectral correlation technique. A question?
Just a quick question. Are you aware of the 3650 megahertz band that the FCC is trying to allocate for cognitive radio? I mean, it's very vague, but
yeah, a little bit.
They're just talking about it recently.
Yeah,
It'd be interesting.
One of our member companies, it's kind of the way we work on that, is that there's some of our member companies who are involved in the standards group. So we have a fellow from Cadence, for instance, who attends I think it's 802.22.
22 is for the TV stuff.
Right.
Yeah, but the one I mentioned is actually under 802.11.
Yeah. Not too familiar with that. So maybe we should.
John Norton. I mean, who's the guy from?
John Notor.
Yeah, I know him very well.
Oh, do you? Okay. Yeah, we work directly. He was just at the center on Friday, so. Yeah, if you have some knowledge of what's going on in the group, we should probably talk about that.
I think that's a potential area for
I mean, what we're trying to do is be a sort of a focal point to bring together as many people as we can.
I may be too naive, but I would think the radar detector people would be good at detecting whether anybody's broadcasting anything. But that's what pays their check.
Yeah. Radar.
No, radar detector.
Radio detector. Yep. The sensing problem is, on the surface of it, well, once you get into it, it gets to be much more difficult because you got kind of over-the-horizon problems. Or the people from Qualcomm were pretty informative about some of the scenarios you have to consider. We're also working on sort of link layer protocols for how you would do this coordination between incumbents and sort of cognitive users. And we're building a cognitive radio testbed. So this is a system that would actually support up to 32 separate transceivers where we can control interferers and potential cognitive users and test out sensing algorithms and control algorithms to control how cognitive users would be able to utilize the spectrum. And the hardware kind of looks like this. We have a number of RF modems, up to 32 of these, and power supplies and so on, into a chassis. And then this thing called this Berkeley emulation engine I mentioned earlier, is a controller for the whole device. And then there's fiber cable between the RF transceivers and the control box. So we have this operational with 4 transceivers now, and are building software to implement various experiments. Okay, so let me talk about ultra-wideband. So ultra-wideband has been a popular subject area for a number of years now. We got involved in ultra-wideband about, I think, 5 years ago when some visitors from Lucent said, ultra-wideband, we think ultra-wideband is going to start to be commercially important, but there's a lot of problems with it. People don't really understand the transmission characteristics of ultra-wideband and signal processing, and so there's a lot of good things to study from a university standpoint. So we wrote a joint proposal. We got sponsored by the Office of Naval Research, and so we've been working on this now for about 5 years. Ultra-wideband has the promises of low cost because of simplicity, integration, and low power. Integration meaning it's basically an all-digital receiver. Certainly if you think about it as an impulse receiver, like this, potential for high input. You can do ranging because it's an impulse system. There's unlicensed operation, and we can hopefully coexist with interferers because we spread our energy out over a very wide frequency, and we can use processing gain to recover it out of the noise. But there's been alternatives proposed, and there's this a multi-band OFDM system, which is basically using a wide bandwidth, the wide bandwidth that's been made available by the FCC, pretty much as a set of conventional receivers. And we think that while that's a better known problem to solve, in other words, people understand better how to build an OFDM system, it really doesn't leverage the benefits of OFDM. That is a pulse-based system. And so our interest has been in pursuing that because you can achieve low cost and low power in a pulse-based radio.
In fact, isn't it true that by modulating to get to that bands where they can operate the ultra-wideband, they're essentially no longer low cost and they're no longer low power?
Well, yeah, that's the debate. And as you probably know, the standard committee is now deadlocked between an impulse-based radio and the multiband OFDM. The multiband OFDM has some significant technical challenges, not the least of which is the frequency hopping, which requires very fast settling
oscillators and synthesizers, and that's where most of the power goes. The most difficult problem in a cell phone is the synthesizer, and where most of the power in a cell phone goes is in the synthesizer to be able to hop, to move from one frequency and to be able to do it with very low phase noise. This multiband OFDM has all of those problems, but I think not worse than a cell phone, but has a lot of those problems. So it's going to be hard to argue that it's low power and low cost, but there are those who are pushing it pretty hard.
I think both proposals, the direct sequence proposal and the MBOA proposal, are both unfortunately designed based on conventional techniques.
Right.
So it's like designing a LAN or a cellular, which is really very disappointing. So I totally agree with you on that. The issue I find with what's going on there right now is that no one is trying to trade so much bandwidth for low complexity receiver. We don't care about spectrum efficiency in this case. And I think maybe that's what you're trying to imply with the pulse radio system.
Right. So, okay, so I got a couple slides here. I'm going to skip over real briefly just because I think you guys are involved, pretty involved in this. But you probably know ultra-wideband devices have been categorized into imaging, sort of vehicular radar applications, and communications. I think this is where most of the interest is in the communications. And the specifications for that band they're in small print for a reason. What it means is there's low power levels, and you're going to have short pieces for pretty much limited to short range. And I think the multiband OFDM people have difficulty demonstrating 300 or 400 megabit per second over more than maybe 10 meters. I think that's challenging. So the 802.15.3a is where all the real activity is. There's a 15.4a, which is sort of a low data rate Bluetooth committee, and ultra-wideband is being considered there.
Well, they're doing well. I think they're going to letter ballot there.
Yeah.
So 3A is deadlocked, like you said, right. But 4A seems like it's going.
Right. Well, they're not as far down the road. Okay, we're interested in trying to exploit ultra-wideband for what we believe is the real benefit, is to build an impulse transceiver that is a 1 milliwatt device, and that's very low cost, that can do 100 kilobit per second transmission. So it's not very high speed. It operates in pretty low, not very high error rates, and over 10 meters. But it's 1 milliwatt, and it's sort of the target application is more for sensor networks. But our real goal is to really understand. Well, first of all, we think it'll be the first all CMOS ultra-wideband transceiver for communication and ranging applications. It's a very aggressive low-power design. It's almost all digital. It's a very simple front end, but it's a test platform to explore ultra-wideband applications. Here's the sort of the architecture. I said it was mostly digital, but this slide doesn't seem to show that. But it doesn't have a lot of complex analog. It's just, there's an amplifier, some gain control, and these are 1-bit A to Ds that are controlled, that are phase controlled through a delay lock loop. It's kind of like a sampling oscilloscope, if you've ever dealt with those. It samples the signal, and then we use a lot of digital logic to recover the signal. We've built the chip, and we actually have it back. It's been fabricated, and it's in testing this summer. So we'll have some results that we'll publish later this year. One of our students is his PhD thesis, and he's hoping to be done by the end of the year.
This is 500 megahertz bandwidth? You mentioned the bandwidth. Is that for 500 megahertz ultra-wideband?
No, it's zero. Yeah, it's 0 to 1 gigahertz band.
Sorry, 0 to 1 gigahertz.
So that there's two ultra-widebands, 3 to 10 and 0 to 1.
Right.
So this is the 1 gigahertz band. Okay, maybe taking longer than I should, but okay, let me move into. I know there's a lot of interest in sensor networks, so let me talk about that. We have a pretty large effort going on in sensor networks. You remember from my first slide, this is sort of that other thrust, okay? And so the work is focused towards deploying an easily deployable, robust, self-configuring, ubiquitous network that's energy self-sufficient.
there's a lot of work going on in sensor networks, and a lot of work going on at Berkeley in sensor networks. And as I mentioned, we're integrated circuit people, so we kind of don't limit ourselves to building prototypes that are based on standard components. So we're really trying to push the envelope, explore the limits of what's possible, and we look at energy, cost, and size optimization at all levels of abstraction. A lot of our work is done here at the physical layer interface, transmitters, receivers, mixed signal circuits, digital clocks are important. And some of the applications are for sensors, for consumer home networks. We have some support from the California Energy Commission, and so in California they want to instrument all houses with time of use thermostats and the ability to provide consumers with information about the cost of electricity, so they can make decisions about whether they're going to use it now or use it in the evening. And so there's some real social issues there that one wonders how you're going to be able to impact the behavior of people. But from a technical standpoint, that's the thinking. So that's the sort of demand response work. There's some work in tire pressure monitors and something called spradios, which are radios that maybe someday you spray on a wall. And so there's some interesting communication theory from a statistical standpoint. Not every radio has to work, and you can make channels out of unreliable systems. And so there's some work there. I won't talk about that. So packaging is a big issue. We're working with mechanical engineering people because a sensor node requires the integration of a lot of disparate technologies, sensors like MEMS devices, integrated circuits, and so on. So there's work going on in that area. Let me just touch on some of the components that go into that. I mentioned oscillators. In communication systems, oscillators and synthesizers that generate frequency references are oftentimes the most power hungry component in a system. So there's been a lot of work going on there. We've utilized, we've worked with Agilent on their FBAR technology. It's film bulk acoustic resonators, which are very nice CMOS technology compatible high Q elements. We've also looked at bond wire inductors and so on. But this is sort of pushing the envelope, a 100 microwatt oscillator that operates off of a half a volt supply. A receiver. Since these are pretty short range networks, they're only a few meters. So we don't need real sensitive receivers. And since we think about these things as being dense networks where there's a lot of sensors, we can build a robust network out of unreliable components by exploiting the statistics of the network. And not every element has to be robust, and we can tolerate fading, for instance, by just routing around the unreliable nodes. A lot of work's going on into that networking and protocols to build robust networks out of unreliable components. The point is that we don't need really good receivers, and what we want is really low power. This happens to be kind of a receiver that uses a resonator and a buffer. It's called a passive receiver, doesn't have any gain, but we can achieve minus 38 dBm sensitivity and useful for many communications, but only 200 nanowatts of power. There's work going on in transmitters, various techniques to build efficient transmitters. So generally transmitters are efficient at their highest power output. And when you start to bring the power down, we don't need a lot of power output. The efficiency goes way down. So we've been able to move efficiencies up into the 30% range, which is pretty respectable, considering cell phone power amplifiers are in that 30% range. You're always faced with the problem of analog to digital conversion and digital to analog conversion. So there's work going on in very low power successive approximation ADCs. less than 5 microwatts for a 6-bit 1 megasample per second ADC that we've built. A baseband signal processor, it's not clear how, at the very lowest powers, how you'd partition between analog and digital. So there's been a lot of work looking at that, and we've built devices that are below a couple hundred microwatts. So in terms of the goal, this energy self-sufficiency, we think that if we can build a complete node whose power dissipation, when it's active, is less than 100 microwatts, we can enable energy scavenging as a means of replenishing a backup battery. And since we don't have to be active very often, it's a pretty low data rate for a sensor node application, that we're getting close to realizing that. Memory is always an issue. If you look at a cell phone chip, and Texas Instruments, one of the leaders there, most of that chip is memory. The actual DSP that does the signal processing is kind of over in the corner, and probably 75% of the chip is SRAM to store things. So low power memory is an issue. We've done some work. See how far you could push down the sort of how much power does it take to retain the data in the SRAM. And now, so as you push it down, you might expect that there's some statistical distribution about which cells maintain their state and which don't. And so there's been work done on that. And now to apply error correction coding to that to allow us to push down even farther. There's a tremendous benefit as you push the supply voltage down in terms of the power dissipation required to keep those cells active. So more work to support that. And then in the networking, level, there's been some good work done by one of our students in controlling the amount of sleep time that these nodes the amount of time that they're sleeping versus sort of querying the network in terms of how long you want to keep them active. So it's sort of a dynamic scheme for optimizing the node lifetime based upon the available energy that node has. Okay, so I'll talk a little bit about some analog to digital circuits and then some of this reconfigurable stuff. I'll wrap up. So this project ties directly into the cognitive radio. I mentioned the sensing problem. So you got to sense this network. And so you have very large signals, you have very small signals, you got a pretty wide dynamic range, and you got to do it very fast. So analog to digital conversion is a key element of that. We got a receiver, we want to convert signals to digital and then process them. So we have a project going on to really push the limits of A to D converters. This is a unique approach in that it uses a very high-speed A to D converter and a slow-speed A to D converter. So you can build a high-speed converter that's not very accurate, or you can build a slow-speed converter that's very accurate. But how do you get both? So this is an architecture that allows you to do that. And the slow-speed A to D converter, it updates the coefficients in sort of an FIR filter for the high-speed, low-accuracy converter. So it's a little bit like a channel equalizer in a communication system. In fact, this circuit here is exactly like an adaptive FIR filter in a communications channel. So we've done a lot of work on this. The design is in layout. We expect to have some silicon in about 6 months. So this, according to simulations, will do a 12-bit, 400 megasample per second A to D converter for less than 500 milliwatts for the analog. The digital is probably another couple hundred milliwatts, so maybe 600 or 700 milliwatts in 0.13 micron CMOS. The best device that's available on the market now is from Analog Devices, and it's 6 watts, which you could never build in any kind of a... You need to get down to this kind of level to be able to enable any kind of reasonable cognitive radio system that's going to sense environment. So we think that that's going to be important. One of our professors, Bora Nikolic, has done a lot of work on power optimization. He's done some consulting work with Intel. You know, when we first started the center, you know, power was always a big issue because we're thinking primarily about portable devices. But of course now power is important to everybody, even people who build fast processors, because more money goes into cooling it than into silicon. So designing efficient circuits is really, really important. One of the students built a power optimizer. So it basically goes and looks at the power delay curve and starts off with initial design, moves down to the optimum power delay product, and then optimizes down to within whatever your power budget is. So we applied that. We built a 64-bit adder using 90 nanometer silicon, and the chips came out. We've tested them. They run. They have 200 picosecond adder delay. They operate off of 1 volt, and so around 5 gigahertz clock rate at 300 milliwatts, which is the best that's ever been reported. This chip actually has, I think, 8 of these 64-bit adders, and each one is designed with a progressively looser set of design tolerances in a means to understand some of the internal interactions of that with regard to supply noise and other aspects. And we're collaborating with some people, Mark Horowitz, a professor at Stanford, on that. But this is a major accomplishment utilizing this optimization network. Okay, so let me wrap up with the reconfigurable computing. Some people have kind of asked, well, why are you pursuing this? And I mentioned signal processing architectures are really important to us. And this has kind of spawned off on some other work that's really been kind of fun, and I'll mention that. We built this Berkeley emulation engine, which was catalyzed by some interaction we did with Lucent when we first set up the center. You know, Lucent is a major manufacturer of cellular telephone base stations, and they've implemented a number of new technologies, and they wanted a platform to kind of test this out. And the emulation capability that was available in the industry wasn't good enough, so they came to us and said, gee, let's work on something like that. And we built this first B platform, which has 20 FPGAs on it, and it'll support 600 GOPS, 16-bit adds. It's pretty fast. But the problem with these things, everybody always points out, is how do you program it? And the programming model that we've used is to use MATLAB and Simulink, which is you're probably all familiar with MATLAB, maybe Simulink. It's a flow-based, communications-oriented, high-level capture and simulation set of tools. And then we built a set of tools using Xilinx libraries that we can directly program this array from that description. We also have a design flow that directly takes us through a set of layout tools to a chip. So we can do, from the same Simulink model, we can build a real-time, it'll operate in real time for most of our applications, cycle-accurate, bit-true emulation of that description, and use that same description to build a chip from. So we've got that emulation, bit-true, cycle-accurate, real-time of the chip. Not exactly logically equivalent, but well, this worked really well, and there's a lot of interest. Gee, we can do bit error rate simulations on this thing in a matter of minutes, where it takes hours on a workstation, and other applications. So some of the computer science people got really interested, and so we built B2, and now we're up to about 2 teraops. One of the things we found out was we didn't have enough memory in the other one. Local memory for the FPGAs. It only had like 1 megabit. This now has, I think, each one of these DIMM slots supports a gigabyte of memory. So there's, I think, 4 gigabytes of memory for each FPGA. And now we're down, you see we have 5 FPGAs. They're a more modern version. And so we've also built analog interfaces for it. So very high-speed A to D converters that we use off-the-shelf. I think they're Atmel A to D converters. So we can do 2 gigasample per second, or so we can do 1 giga. We can oops, we can look at a 1 gigahertz bandwidth signal and process it on this thing. Well, some of our friends from the Space Sciences Lab, this is interesting. Maybe we could use this for radio astronomy. This is kind of where the funds come in. But let me point out, our interests are in architectural exploration for future radio SoCs, systems on a chip, emulation of the performance. So we're looking at sensor networks. You want to be able to emulate a large sensor network and look at it over millions of cycles. You can't do that on a simulation platform. Algorithms for software-defined radios and cognitive radios, I mentioned that. There's also some interest in CAD acceleration. The blue is interest for other people have come to us, FPGA place and route, optical proximity correction for masks, which is a very compute-intensive application. So our radio astronomy people have come in and said, this is a search for extraterrestrial intelligence. I don't know if you're aware of that. It's a big center at Berkeley, and I guess they have the largest computer network in the world with this SETI screensavers where you can help them process their data. And then other scientific applications. So this has kind of been fun. I want to kind of wrap up with this. So we got involved with these SETI guys, and you may be aware that there's this Allen telescope array that's being built in Northern California. It's going to be sort of this, I think, the state of the art for radio telescopes. It's a square mile array of low cost. What are these? I think they're 4 or 5 meters. So we've been working with them. So the problem is to build a spectrometer that has 0.7 hertz channel and over a 800 megahertz frequency range. So it's a billion channel spectrometer. And it turns out you can program that up on one of those boards. A 1B module operates at 333 GOPS and 150 watts. It's kind of like a desktop computer. And so it's the reason we're interested in this because these kind of architectures achieve like 100x improvement in terms of speed power over a programmable architecture. And so we actually took it up to Hat Creek where they're building this array, and inside the building. And here's our B2 board with this analog interface. It uses a high-speed InfiniBand connectors between the board and the front end. So we've got I think each one of these support 3 gigabit per second. So actually implemented that billion channel spectrometer. So that's been a lot of fun. Okay, so let me end here. Our center started in '99, so we've been in operation about 7 years. And we've established a public domain research model, as I mentioned earlier. And we've been able to successfully collaborate with a number of industry members. I mentioned this, a number of our projects have been catalyzed by that interaction. Our work in ultra-wideband, our work in this B and reconfigurable architectures. And we really encourage companies to get involved with us and try to influence in the direction and interact with our faculty. We now have 17 members, 60 graduate students, been pretty constant. Graduate students come and go, hopefully. About a dozen faculty. So we have semi-annual research retreats. They're for our member companies and our researchers to sort of present our most recent results. We invite guests, and we'd be happy to have some Microsoft people come. Victor attended one of ours as a guest. We'd hope that maybe you can get involved with us as a member. I encourage you to look at our website because virtually all we do, as I said, is public and it's on the website. And there's links to all the researchers. You can talk with them. We've built an infrastructure that allows us to do world-class SoC research, CAD tools, emulation engine. We have a library. And most importantly, what we do is when we're
We're an educational institute. We've graduated over 80 students, about more than half of them PhDs. Actually, one of our recent PhDs, Brian Otis, just took a faculty position here at the University of Washington, and he was one of the leaders in this low power RF work for the Pico radio work. So, thank you for your attention, and I think I'm going to be around in the afternoon, so I'm happy to answer questions and get into whatever discussions. Thank you.
I guess in the questions we can do are...
I'll do, but I'll wait for the afternoon meeting. I think will be awesome.